Alright, so this is going to wrap up our linear systems of equations lessons. Now we're going to do the next two examples and then we're going to call it good. So example 14. So example 14 reads, the admission fee at a carnival is $2.50 for children and $7 for adults. On a certain day, we had 1,400 people attend the carnival, and the admission fees totaled $5,822. We want to know how many children and how many adults attended the carnival that day. So I'm going to start this by saying that C can represent the number of children, and A the number of adults. If I do that, then I know if I take C and I add A to it, that should equal the total number of attendees. And we had 1,400 people in attendance. So C plus A equals 1,400. Now if I multiply each variable by the cost of a ticket for that person, we can set that equal to the total amount of fees they brought in. So if I go 2.50 times C plus 7.00 times A, that can equal 5,822. Now we can do elimination, we can do substitution, it doesn't matter, it's up to you what you want to do. I, though, in this example, I'm going to use elimination. I'm going to multiply, I'm going to eliminate my C term. So I'm going to multiply everything in the first equation by 2.5. So I can do that. So we're going to have 2.5C plus 2.5A equals 3,500. And then we can just rewrite that second equation. 2.5C plus 7A equals 5,822. Now I'm going to actually multiply my entire top equation by -1. That's what I'm going to subtract. My C terms are gone. I'm going to be left with 4.5A when I combine my A terms. And I'm going to have 2,322 when I combine my constants. If we divide by 4.5, we'll be able to find A. So A is going to equal 516. Now what we know from our equations we set up, if we go C plus A, so C plus 516, that should equal 1,400. So if we subtract by 516, we can find that the number of children in attendance was 884. So that means on that day we had 516 adults and 884 children. And that wraps up example 14. So let's look at example 15 and then we can call it good. We'll skip 16 and 17. So our last example reads, it took Brett 2 hours to fly from Philadelphia to Pittsburgh, a distance of 260 miles, flying into a headwind. Just as a quick deal, a headwind means the plane's going against the wind. Following the same flight path, his return flight was 1 hour and 15 minutes. If the wind speed and direction was the same for both flights, find his speed in still air and the wind speed. So what that means is, if we're setting up all of this, I'm going to have two variables, and I'm going to use x and y this time. X is going to be the plane's speed, y is going to be the wind speed. So, if on the way there, it took him 2 hours going against the wind, meaning his total speed would have been the speed of the plane minus the speed of the wind. We can multiply that by 2. That should be the distance he traveled, 260. Now on his way back, he had the wind at his tail end. It was pushing him. So we can take x and add y to that. But this time it took 1.25 hours. 15 minutes is a quarter of an hour. Equals the same distance, 260. So what I'm actually going to do first is I'm going to divide by 2 in the top equation, and I'm going to divide by 1.25 in the bottom equation, just to make things a little easier. That's going to give me x minus y equals 130, and x plus y equals 208. Now, my y terms are already opposites, so we're going to just add straight down. We're going to have 2x equals, well, 130 plus 208 gives me 338. If we divide both sides by 2, so 2x equals 338, divide by 2, I'm going to get x equals 169. So, I'm going to go and I'm going to say, we know x minus y, that has to equal 130. We know x is 169. If we subtract y from that, that has to equal 130. So if we subtract by 169, we're going to get negative y equals negative 39, which means positive y equals positive 39. So that means the plane's actual speed if the air was still was 169 miles per hour, and the wind speed, in this case because the wind was not still, was 39 miles per hour. And I said we could end after example 15. I'm going to stick to that. We are done with linear systems of equations.